So a lot of what you read had a lot of jargon and terminology. And I thought it would be fun to start by getting on the same page in terms of that terminology. So when we talk about the quantum realm, let me use Lisa's term, quantization is a really big concept. So can someone tell me what they think of when they think of quantization and why it might be important for us? In the quantum universe, you can only access discrete energy states. So in our everyday world, I'm standing here, and I walk over here, and that is a continuous process. I don't just suddenly appear here. But in the quantum universe, electrons can't do that. They can't continuously move from one energy state to the next. They appear at each of them. So what's fun about this for us is that this quantization of energies of electrons and other particles, it's really useful for encoding information in a binary digit system. So the ground state of my atom or whatever particle can be the 0, and the excited state can be the 1. And what you're going to see is a lot of the qubit systems that we're going to look at work exactly like that. You're using the ground state as 0, and you're using some excited state as 1, and you're doing something to push between them. The handy thing is that the ground and excited states can be our binary digits. All right, so where things get weird is when we think about this aspect of quantization and the idea of superposition. So what is superposition? That's something we talked about last time, and it's critical to understand for this class. So what's superposition? Yeah. Yeah, or it can be both. It can be 0 and 1 at the same time. So this fun little animation is from NIST, and it was in the Soto article, and it's showing skateboarder and saying, okay, skateboarder's here. But in a quantum universe, it can be in both places until I look at it, and then it collapses to one of them. So yeah, superposition is the ability, and it's not really exactly being in two states at the same time. It's being in a linear combination of states at the same time, where the coefficients of that linear combination dictates the probabilities of being in one state or the other, right? So that was our A and B coefficients in our wave function last time. David Wineland, who received the Nobel Prize in 2012 for his experimental work in this field, he gave the analogy of superposition as, so he deals with trapped ions, which we'll hear about from Sarah later in the class. And he gave the analogy of his trapped ions being a marble in a bowl. So the marble can roll back and forth, and in normal times, it will be on one edge of the bowl, or I'll roll it over to the other edge, and it'll be there. But what's cool with these trapped ions and other qubit systems is that you can create a scenario where it is in a superposition of both states. That is what allows it to act as a 0 and a 1 at the same time, whereas ordinary bits of data can only be 0 or 1 at any given time. That's why qubits can hold more information, exponentially more information than a traditional bit. So the problem with superpositions is that they're very fragile. They don't hang around easily. Doing anything to them can potentially break them. Certainly measuring them breaks them, right? We know that. That's kind of by definition. But there's lots of other things that can, break my superposition. And those things are generally called decoherence. So anything that breaks my superposition. So it's something in the environment. It could be something even in the qubit itself, not to mention, temperature or something in the environment that causes a superposition to be destroyed. So you're saying, okay, I'm not measuring it directly, but I might be observing the system heat up, or I might be observing light move in a goofy way over here. So I'm kind of indirectly observing it. So that you are influencing, you're perturbing the system. And those are the things that can potentially break the superposition. They're also the things that are potentially interesting about the superposition. So it is, yeah, as we'll see more, it's quite delicate. And that's why nearly all of these systems operate at, the non-optical systems at least, operate at really low temperatures, like dilution refrigerator temperatures below helium. Yeah, it's interesting, this issue that you're bringing up in traditional computing as the size of gates gets smaller and smaller and smaller, we get to nanometer separations between gates, and so then they kind of become quantum because tunneling becomes kind of operational at those length scales. The last, maybe most weird, big buzzword in all of this is entanglement. And so that's this sort of quantum marriage between qubits. Somebody want to explain how they think about entanglement? So two particles share some fundamental part of themselves so that no matter what distance they are from one another, particle 1 influences what particle 2 is doing. So imagine you have an ion, this like trapped ion acting as a qubit, and it's in a superposition of 0 and 1, and I entangle it with a second ion that's also in a superposition of 0 and 1. The two entangled ions are going to maintain this special relationship even if they're separated by a really large distance from one another. So as an example, if this kind of weird relationship can mean that the two particles will end up in the same value, either 0 or 1, when I measure one of them. So measuring one of them impacts the state that I'll measure for the other one. That's pretty weird. And I think some of you may have heard this term that Albert Einstein coined long ago called spooky action at a distance in quantum mechanics. And this is the kind of thing he was sort of describing. So if I measure the value of one qubit and it determines the value of my second qubit. And that's why in quantum information, having one qubit by itself isn't actually very useful because it is 0 or 1 when you measure it. But having two qubits, I can measure one of them and I haven't touched the other one, so it can still do useful things for me. It can still tell me about the first one, even though I've measured it. All the A, B, theta, phi, all those fun variables. Yes, okay, so quantization, superposition, decoherence, and entanglement. Those are kind of the big things that we're going to discuss in this course over the next several weeks once we have our bearings about us. All right, so there are some other fun terms that were brought up in some of these